Worked. Okay, so thank you for that introduction. My name is Ellie Hara, and today I will be talking to you about releasing cyanide from ferrocyanide by carbon monoxide ligand exchange in alkaline aqueous environments. This is one section of my PhD that I'm presenting today, which was just completed this past fall. So the first thing I want to talk about is the way I think about the early Earth and the way I think a lot of the Templeton group thinks about the early Earth, and I would say a lot of geochemists is when I think of the early Earth, I think of that they're about how there are these lots of ultramafic and mafic rocks that are undergoing serpentinization. And this is the kind of geologic environment that I'm really interested in. We think that these environments were widespread on early Earth, and they have been proposed as important environments for the origin of life. Serpentinization is simply a hydration reaction that occurs pretty much everywhere. And we don't see it just restricted to early Earth and modern day Earth, but we think that serpentinization may even be occurring underneath the European oceans or Enceladus oceans, and there's evidence of past serpentinization occurring on Mars. In this reaction, you have olivine and water that react, and then we get the formation of serpentine, brucite, magnetite, and hydrogen. That hydrogen gas in particular, along with the minerals that are in there, kind of combine to make it an intriguing place to study the origins of life. When serpentinization occurs, that fluid becomes hot, it becomes rich in metals, it becomes an alkaline pH, and there are areas in serpentinites where that water will escape and come into contact with that cold, much more acidic ocean. And that leads to these formation of chimneys where it's a precipitation that occurs when these two different water chemistries mix. And this is a picture of the Lost City hydrothermal vent. And it's this beautiful, very charismatic structure of like, wow, there's, bubbles going and there's a lot of life that lives there. But when we think about early Earth, we're not getting all this complex life that currently lives there. And instead, a hypothesis was and framework was kind of drawn up around these systems. So Mike Russell was one of the first people to really talk about this, and he's kind of continually edited and revised this hypothesis as we learn more about these environments. There's also been some great experimental work kind of trying to work on some of the things, but the entire principle of this framework is that there is a pH gradient, there is a chemical gradient, and there are temperature gradients that kind of provide some sort of like power to push reactions forward. And these natural gradients lead to chemistry. And the chemistry that they've really focused on is like life's first metabolism. And when I remember talking to Mike about all this, he's like, well, you need the engine to drive the car. And that's what he always tells me about. And he's lovely like that. And so they really honed in on the Wood-Lyngdal pathway, which is also known as the reductive acetyl-CoA pathway. And it's a carbon fixation pathway where we're getting that inorganic carbon to organic carbon. And they like the Wood-Lyngdal pathway because it's considered one of the oldest metabolisms when they do metabolism with like phylogenetic reconstructions. And in this hypothesis, something I've been very interested in is the act of minerals acting as like a proto-enzyme, meaning like a pre-life enzyme, kind of acting as that. Now, that is what the rest of my PhD was focused on. But today I want to actually talk about something different. And that's because this has been recently published in ACS. And when you get into grad school, I come from this framework. This was the framework I was learning. You read about all the other things. And this is where I was like, wow, it's interesting that this biosynthesis box is kind of like, biosynthesis. But then I got to read all these other things, from the RNA world people that are doing incredible work. You read about the cytosulfidic world. I was like, wow, there's this whole other side of chemistry that is not currently being integrated into this framework. And, if I'm a geologist, I like this kind of system. What can we do to kind of fill out this biosynthesis box? And one thing that I realized is that, well, this alkaline hydrothermal vent system is actually not considered any cyanide chemistry. And cyanide chemistry is so important. And as someone who's been, really trying to gain more skills in organic chemistry and biochemistry, I'm like, wow, cyanide is such an important molecule for prebiotic chemistry, and we're just not using it. And so I feel like this audience will know this much better than me, but cyanide is a strong nucleophile capable of many different organic chemistry reactions. You might have your favorite. Some things I want to highlight are Strucker synthesis for amino acids, or synthesis of nuclear bases, and Eschenmoser synthesis for ribose-like sugars, and also just all these incredible prebiotic networks that people have modeled and demonstrated. And cyanide is something that can be formed in the atmosphere through photochemistry, and can be delivered from the interstellar medium from meteorites and comets. One issue with cyanide, though, is that it can hydrolyze, and there goes our cyanide. Oh no, we wanted to do work. There it goes, bye-bye. But so then this question is, how do we accumulate enough cyanide to do the work that we want to do? And Keefe and Miller proposed that, well, cyanide will get locked into ferrocyanide, and here's a really useful concentration method. So ferrocyanide is a iron 2 6-cyanide ligand complex. And when cyanide is in the presence of ferrous iron ions, it will spontaneously form these complexes. I put up the equation there just to show you that K equilibrium, which really shows just how favorable this complex is. And if we're thinking about an early Earth environment, hey, there's a ton of iron 2 around to kind of trap this cyanide. So, hey, we've concentrated that cyanide. We made a nice little packet. However, there is a problem. When cyanide is locked into that ferrocyanide, we can't do work with it. It's kind of like, oh, I'm happy, I'm going to hang out here. We need to get that cyanide out of that system. And this is where the strength of that complex becomes a double-edged sword. Really great for concentrating, not so great if we want to use that cyanide for work. There are current suggestions for releasing cyanide from ferrocyanide. One is UV light degradation. One issue with that is the second you remove the source of UV light, it kind of reforms very rapidly. It also doesn't really work if I'm thinking about a subsurface environment, my serpentinite, my under the ocean. We're not getting that UV light penetration. The second thing is that it doesn't really decompose that a high of a percentage of your ferrocyanide, so you're just not getting a ton of release. Another hypothesis is thermal decomposition. And this is, I think, one of the key players in the cyanosulfidic prebiotic network system proposed by researchers like Sutherland and Sasolov in that. And in there, what they have is a bed of ferrocyanide salts that have been dried and then get impacted by a meteor. And that needs to get up to like 600 plus C to break apart that ferrocyanide. And I also include that temperature to be like, wow, this is a really stable complex. Like, it's hard to break it apart. We propose instead that carbon monoxide can actually replace cyanide in this complex through a ligand exchange. And so here is our ferrocyanide structure here, and here is a carbon monoxide, and all it's going to do is knock off one of these and release a cyanide. And then you might be like, well, why are you using carbon monoxide? This is a table of ligand strength that I've just pulled from a general chemistry textbook. Yes, it changes, but essentially cyanide is a very strong ligand and very few things are stronger. Granted, I know ligand strength, yes, it's dependent on condition, but we need a strong ligand to kick it off. But the other thing is that carbon monoxide is not this exotic molecule for early Earth. There's multiple sources where we can get this carbon monoxide to drive this ligand exchange, whether it's through volcanic emissions, formation in the atmosphere from impactors, or even within serpentinization from the reduction of CO2 to CO. And so I'm still in this serpentinizing environment, and what we did was we tested this ligand exchange. And this is what our experiments look like. They are just in anaerobic serum vials. They're wrapped up in foil, so we prevent any UV light from getting in to kind of isolate this system. And in each of them, we just added 0.1 millimolars of ferrocyanide, and the composition of that water is not just plain DI water, but it has salt added to it to be designed, and it's designed to simulate the groundwaters that are in equilibrium with these serpentinizing environments. We kind of base that off of the field work that was done by the Templeton lab in Oman, just these types of waters. And Tristan will tell you more about the types of waters in his talk. So we're in these systems, and what we did was just measure, hey, that ferrocyanide concentration. And so anytime we add carbon monoxide to the system, that ferrocyanide decreases to 0 all the way down. It is faster in the alkaline system and then hyperalkaline, but we had 5 replicates, and we can see that carbon monoxide in our controls are looking real solid. So this is great evidence. Hey, it seems like when we add CO to the system, this ligand exchange is occurring. We're changing that ferrocyanide out. We're putting that CO in. We're getting a ferrocyanocarbonyl complex. And we're like, great, awesome. We did this with a 0.05 atm partial pressure. And we're like, can we go lower? Is it possible that we can do this even with less and less amounts of CO? And so the next experiment is we took our faster system, the alkaline 9.1 pH, and even down to 0.0025 atm, we still were able to see this effect of the decrease of ferrocyanide over time. And what that tells us is, wow, even though it's slower, this reaction seems incredibly favorable. So it kind of points us to the direction that if there's ferrocyanide and there's CO, well, this ligand exchange is going to occur, and there's going to be an equilibrium that forms between these states. And we're like, awesome, yay, this is great. But this doesn't answer the question necessarily, because why did we want to do the ligand exchange? Well, we want to do work with cyanide, right? If we release that cyanide, but it's not able to react, well, dang, that doesn't really help us. So that was the next question we tackled. Is the cyanide we release from the ferrocyanide free to participate in downstream reactions? To do this, we added polysulfide to the system to see if we can form thiocyanate. Now, polysulfide and thiocyanate, that was not chosen out of a prebiotic reason. That was mainly chosen for an analytical of like, it's a known simple system. And the second we start adding organic molecules, it can get very, very complicated. And we were like, no, we just want to make sure that the cyanide can do other things first, keep it simple. So this is kind of the generalized reaction, right? We have some amount of CO that's able to replace and kick off cyanide, and we want to see if that cyanide can make thiocyanate. And to do this, we went to the Raman system. So this is our Raman data. And what we did was dry down the experiments and measure the powder with our green laser. And down here are our 2 thiocyanate standards. And up here are our controls. So these are all the systems, with sulfur, without sulfur, with cyanic CO, without CO. And this is our experimental system. And what we can see is when we have both polysulfide and carbon monoxide in the system, we're getting that formation of that SCN peak. Therefore, we're like, hey, this is great. We made thiocyanate. This indicates that we're not only are we knocking that cyanide out, we're actually able to do work with it, which is awesome. So to conclude this section, at times we're going to have CO and CN that are going to be able to exchange in our prebiotic environment. And we did all this at subboiling temperatures. So I, like to imagine this bed of just water coursing through the serpentinite and being like, okay, we can do this kind of chemistry. And I think what my favorite result of this is that not only are we doing this, we're able to do reactions with that cyanide we release. So we're releasing that cyanide, we're making different types of ferrocyanocarbonyl complexes. And what I always like to state is that this chemistry doesn't preclude any of the other methods that were there. And I always see this as, hey, we can slot this kind of chemistry into multiple environments and multiple systems as a way to get a continual bleed of CN, because ferrocyanide and CO should be available in these environments. And so the framework I'm most familiar with is this Lost City system that I've been thinking about a lot. And I'm like, okay, well, let's try to use this as a plausible chemistry to be like, okay, we do have a source of cyanide. Let's try to see if this makes logical sense and build out this framework to include more biosynthesis. And this is something that I'm trying to write up for a hypothesis paper. So hopefully that, you'll see that sometime soon. And the second thing that I'm going to add in there is that, okay, I've talked about all this stuff. The second thing I want to zoom in on is actually this complex here. This complex, the reason I first got interested in it was because it was found on the Lewis Cliff meteorite, and that was in a paper by Smith et al. In Nature Communications. And something that they noted was that structurally, the ferrocyanocarbonyl complexes, the way that iron has this two cyanides and the carbon monoxides, is structurally similar to the iron-iron and iron-nickel hydrogenases. And I was like, wow, that is super cool. And now that I have a way to, make these ferrocyanocarbonyl complexes in the lab, I'm very interested in, characterizing them and being like, okay, I know this is just a simple complex. How close can we get to the functionality of a hydrogenase with just adding these ligands? Like, what can that thing do? Is there any sort of chemistry that the ferrocyanocarbonyl complex can do because of that ligand structure? And then kind of zooming out of just that complex is, well, I've been thinking about minerals and working on mineral facilitated reactions, right? That's what I've been doing in the lab when I'm not working on this, is we look at the metallocenters of enzymes and we're like, wow, okay, let's take that metal bit and see if it can work. But biology has so much more attached to that metal bit, right? That it's doing that work. So are we overall overlooking ligands and, things being bound to the mineral surface as a key part of getting us closer to the structure and maybe even the functionality of that, proto-enzyme? Like, do we need to start adding a cyanide ligand here and there, or a carbon monoxide ligand, or these other things on the mineral surface to get us closer to like a proto enzyme or like a pre-life enzyme? So that's kind of my very like out there speculation thing. And I feel like I can't do a prebiotic chemistry talk without some sort of speculation. But with that, I'd like to acknowledge where I've done this work, which is, the Templeton Lab Group and the larger geobiology collective at CU Boulder, my funding sources. But I'm also really happy to continue doing this kind of work, looking at ferrocyanide and mineral facilitated chemistry. I'm starting a postdoc at the Rare Institute at Rensselaer Polytechnic Institute in about 3 weeks, working with Professor Kristen Johnson-Finn. So super stoked to continue thinking about these kinds of chemistries. And I'm just shameless plug, put the title of that paper there if you want additional details and things like that. So I'll just leave it on this conclusion slide and happy to take questions.
Thank you so much, Ellie. That was fantastic. And my goodness, congratulations on graduating and the paper and having a postdoc.
Yeah, it was a push in the past like 6 months. It was a lot. And then I was like adjuncting as well for the first time. I was like, it's a lot. So
oh my goodness.
Well, it was a fun semester.
Impressive. Yeah,
no,
for sure.
It was a lot.
All right, fantastic. I think what we'll do, if it's okay, is we'll have Tristan give his talk and then we'll do questions at the end. So if you have questions for Ellie, please remember them. And then we'll come back to do questions at the end. But thank you again, Ellie. That was so fantastic.
Thanks. Let me make sure I can get out of share mode.
Sounds good. Oh gosh. Yes, it's still very difficult to use Zoom, right?
It's been years and
Yeah. All right. And now we're going to have Tristan Caro give a talk. So he again is at